Thanks for the introduction. So I'll be talking about really my work towards developing a hardware embedded boundary method. So the application space that I work in is generally modeling fluid flows through a variety of different applications, whether that's things like looking at turbines or ice sheet movement, or flows through bio-inspired materials. And kind of the common theme with all these things is the interesting physics at play are that we're looking at flows that are kind of governed by their interaction with some kind of complicated geometry. And really, as a person who builds the models and looks less at the application, is in trying to make this kind of thing relatively easy to do. Both in the sense that it makes it relatively simple to set up a model, and so you're not spending days doing it, hopefully, and then once you send it off to some large computer, you can get a result back in a decent amount of time. And the general approach for these kinds of things is that we have, for whatever region our fluid flows through, some kind of a grid where we store in each number of cells what our fluid state looks like in that region. And so to make this, hopefully computationally efficient, we look at structured grid approaches where we ultimately have some kind of a Cartesian grid that we perturb or distort in some way to represent whatever complex geometry we have of interest. And the reason being is that these things are relatively easy to calculate information on, and we have tools that adapt measurement to target where our computation happens. So for things like this flame front I've got an image of here, we can really refine automatically around regions of interest where physics are happening, and then in coarser regions can do far less computation there. Now, if I want to make actually a grid around something more complicated, or in some case this triangle here, the approaches for this are generally things like the mapped grid approaches, where I can take a number of Cartesian blocks and I can warp and distort them and I can stitch them together in order to create grids around this simple triangle in this case. And when doing so, the user who actually does this has a lot of control over what the grid looks like, which is kind of a blessing and a curse. You can really control the grid when it matters, and if you know something about the flow, you can tailor it to that. But doing so takes a lot of time. And so we instead look at embedded boundary methods, where we take a bit of a different approach and take just a purely Cartesian grid and just embed our geometry in here and cut around the boundaries, since we get a number of oddly shaped or irregular cells on these boundaries we've got to deal with. But the big advantage to doing this is that making these kinds of grids is entirely automated. You can more or less import a CAD file, and there's really no restriction to what level of detail you can capture with these things, which is generally not the case with mapped grids. Embedded boundary methods are not a terribly new technology. They've been around for a while, but what is new is doing these things at high order accuracy. And why this matters is that if I have some given solution or flow or solution for something on a given grid, and I want to increase the accuracy of this, the only way to do this really is to increase the number of cells in my calculation or in my computation. And if I'm doing something that is second order accurate, for instance, if I double the number of cells in my solution, I reduce the error in that overall solution by a factor of 4. And if I do something that's higher order, so fourth order, for instance, a doubling in my number of cells reduces the error in my overall solution by a factor of 16. And so if I want to decrease my error more rapidly, a higher order solution can do that. And for example, if I have, and can do it with fewer cells. If I have some target error where I'm looking at maybe six digits of accuracy with a second order solution, I'm able to do the same thing with a fourth order solution or fourth order method using something like a factor of 1,000 fewer cells for the same problem. Now, this doesn't come for free, and so we actually end up doing a lot more calculation per cell in order to make this happen. But that's not entirely a bad thing. Modern computer architecture is moving towards things like GPUs, where we've got tools that are really good at doing a lot of calculation and don't like moving data around a whole lot, which is kind of the problem we've set up with high order methods. So in order to actually make this happen then for these finite volume methods for embedded boundaries, we use, again, a finite volume scheme where we use a least squares reconstruction to actually evolve this. And so if we zoom in on some example grid here, for an embedded boundary method, we have something where we've got some boundary here that is potentially arbitrarily curved. And away from this boundary, we have regular cells where calculating things is relatively easy. And on the boundary, we have these partially sized cut cells with curved boundaries, and they can be arbitrarily small potentially. And we take a finite volume approach for this, where in each cell we take a control volume approach where we have some kind of a average quantity for what our fluid state looks like in that cell, and we evolve this in time by constructing fluxes for how our fluid state moves from one cell to another. And by doing this, we've got something that's naturally conservative, so we've preserved things like conservation of mass in our flow, which can matter. And And if we want to do this thing at high order, really all the work comes down to how do we construct these fluxes for flows between one cell and another in a way that is sufficient or produces the order of accuracy we're looking at in the presence of these cut cells where geometry is a little more challenging. And the approach we take is to use a least squares method, where in some 1D example, we might have a set of data in our cells at snip at a time with this blue solution. And if we want to construct a flux for this, where we might need to calculate like a gradient or higher derivatives, we can do a least squares interpolation on our known set of data to produce some polynomial, and then use that to evaluate our fluxes as needed. And the benefit to doing this with a least squares method is that controlling the order of accuracy is relatively simple. We can do this in a way that's dimension independent, so we can use the same method for anything from first up through third 3 dimensions. And the least squares method really doesn't care too much about what the data layout looks like, and so it's robust in the presence of cut cells, as long as we have a sufficient amount of data for our interpolations. So we can do the same thing then in 2D, where if I have some face ultimately that I need to construct a flux about, I can grab just some neighborhood of data for this where I prioritize setting things that are close before things that are far away, do a least squares interpolation, then evaluate my fluxes. And I can do the exact same process with something in the presence of an embedded boundary method where this face is potentially cut and smaller. I've got cells that can be quite a bit smaller than others, and I might have things like boundary information that I want to include in this kind of my recent reconstruction for my fluxes. So I can take this and then apply this for more general applications. And to verify that we actually have something that's doing what we're targeting, we can look at Stokes flow as an example test bed. We're looking at flows that are very generally slow moving and dominated by the stickiness of the fluid. And the nice thing with these kinds of flows is we have exact solutions we can compare to, making it easier to verify that our algorithm does what we intend. And we see that we do actually produce all the right kind of properties. So we do get the order of accuracy that we're claiming to have. We can analyze errors for this and see if the errors are dominated in our embedded boundary cells or the cut cells, which is expected, but these don't contaminate the rest of our solution globally. And then we have stability properties. So small cells aren't, as cells get smaller, they're not giving us surprise issues with our solutions, which is a kind of common challenge with embedded boundary methods. We can take this and apply this also to more complicated cases where we don't know exact solutions, like this kind of bio-inspired material that I had shown originally. And with this, overall, we're able to do this kind of complicated thing where the grid is entirely automated for us. This would be a real disaster to do by hand. And we're able to then solve for this and have flows that we're qualitatively quite happy with, and do so in the presence of some cells that are really quite small with this. So we zoom in here. We get these little slivers of cells potentially that are, with some of these being on the order of about a 10,000th of the size of a full Cartesian cell. But despite these being really terribly small, we're not doing anything special to treat these cells and able to still evolve our solution and have things that are stable and make sense. So overall, quite pleased with how this is developing so far. I'm excited to take it and apply it to more applications. But as someone who works a lot more on the model development side than the application side, I think kind of areas of interest for me is actually combining these embedded boundary methods with things like map grid approaches. There's applications like things like modeling turbine vanes where, in general, the geometries are very smooth, and being able to create a grid around this makes a big difference in how accurate a solution you can produce. But in reality, we might have things like cooling vents to keep these things working, or screws, or sharp edges that actually have to happen in practice. And modeling these can make a difference in what the flows look like around these things. And so ideally, we could do something where we use a map grid approach to get kind of the large scale features that we can tailor things around, and then fall back on embedded boundary methods to capture kind of the fine details when we have to, that it would be hard to do otherwise. So thanks everyone for being in my talk today. If nothing else, I hope one part of that embedded boundary methods are a great tool for doing complicated things. And if you're looking at that, it's a technology worth exploring. And if possible, higher order methods are generally a good fit for larger computers. And certainly need to thank Hans Johansson, who's been really instrumental in this work happening so far, and open it to any questions.
Thank you for the nice talk, Nathaniel. Any questions from the audience here in the auditorium? Yep.
Hello, thank you for the talk. So my understanding for embedded boundary methods is the reduction of the order of accuracy at the boundaries is usually the concern. So is it the least square construction which is the key to preserving the order of accuracy at the boundaries, or is it the numerical scheme itself?
Yeah, so it's all that least squares construction is really what does it. So we can create a fourth order construction at our boundaries, and we use the same thing interior. Is the idea?
So the least square construction is on the flux, or it's on the...
Yeah. So if we have our solution, we would on a face we construct something. We construct a polynomial local to the face, and then we can evaluate that. So if we need a gradient on that face, for instance, we can construct a face averaged gradient using that polynomial, and we do this individually for each face in our solution.
Thank you.
Yep.
Other questions? Maybe online. Any questions? Okay.
So in all your examples, I think your cut cells were either concave or convex. What if you get more complicated geometries? Do you just have to refine the Cartesian grid?
So we do round things slightly right now to so if I have a sharp quarter in there, that's just a little bit too much to handle. So we round those right now, but round it based on the cell size. So if you continually refine, you approach whatever sharp feature you have. But we can't have multiple cut faces in one cell, for instance. It's not something we've explored quite yet, but it's on our radar for sure.
Great, thank you.
Yeah.
Okay, if there are no more questions, let's thank Nathaniel again.